Okay, class, I decided to start making videos of the PowerPoints so we have them as reference and can share them with other classes. So this is Miss Miller recording, but if you aren't in my class and are listening to this video, welcome. I hope it helps. So there are 4 sections in the review chapter that I want to cover, and the first one is just Algebra Essentials. This is stuff that I just want to make sure we are nice and refreshed with the terminology as we proceed in this course. So friendly reminder about the different number families. So we're going to be working with real numbers, right? Real numbers are the numbers we encounter in our everyday life. Those include the natural numbers, which are also known as the counting numbers. Those are 1, 2, 3, 4, 5, and so on. The natural numbers plus 0 gives us the whole numbers. We get the integers by taking the natural numbers, 0, and the additive inverses, otherwise known as the negative whole numbers, of the natural numbers. We also have all of our rational numbers. These are any number that can be written as a fraction, also known as a ratio. This also includes decimals and things like that. Now, friendly reminder that any integer is also a rational number, right? It can be written as a fraction over 1. We also have the irrational numbers. So that's any number that can't be written as a fraction. So for example, pi can't be written as a fraction. Square root of 2 cannot be written as a fraction. That's true for the square root of any primes. Complex numbers is all the real numbers and imaginary numbers. Remember, imaginary numbers are square root of negative 1, right? The square root of negative 1 also denoted I. Descartes, right, who also developed the Cartesian plane, the XY coordinate plane, he coined the term imaginary, but we aren't working with these just yet. For now, we're just going to live with the real numbers in the real number line. Here's the containment if you wanted to see how the real numbers, I was about to say added up, but how they're contained in each other. So counting numbers, then we add 0 and get the whole numbers, then we add the negative numbers and we get the integers, then we add in a whole bunch of fractions and get the rational numbers. We also take our irrational numbers like pi and the square root of 2, and if we group them all together, that gives us the real numbers. When we have real numbers, we can represent them on a number line, right? So like I said, we've got our whole numbers, natural numbers, integers, rational numbers, and our irrational numbers. And we can represent all of those on the number line. When it comes to inequalities, that's a way for us to compare numbers on the number line. And we can compare them with numbers like less than, greater than, less than or equal to, and greater than or equal to. Linear inequalities are like equations, except instead of an equal sign, they use these inequality symbols. And what's different about them is they can have many solutions, right? And so we need to graph these solutions on the number line. I'll also show you how to write them in set and interval notation. So here's a few examples of these symbols in action. When we're solving an inequality, what we want to do is we find the set of all numbers that make that inequality a true statement, right? And we're going to call that set the solution set. And all those numbers would satisfy the inequality. So for example, if I have x is greater than negative 2, what could my values of x be, right? I could have x is 5, 7, 1, 2. It goes on forever. So we need to find a better way than just listing all possible solutions for this inequality. So what we're going to do is we are going to, let me go ahead and graph this and we can practice. So let's say x is less than 3. Now 3 is not part of my solution, right? Because 3 is not less than 3. My solution is all values of x that are less than 3. So I'm going to be shading to the left, right? Because 2 is less than 3. So now I can write this in interval notation. So interval notation is when I write this in between parentheses and brackets. So square brackets are used to indicate that endpoints are solution. This is our endpoint, and it's not part of the solution, right? Brackets are used with greater than or equal to or less than or equal to. Parentheses represent endpoints that are not solutions. That's what we have here. So that's used with greater than or equal to or less than or equal to. It's also important to know that parentheses are always used with negative infinity and positive infinity. Negative infinity is what's all the way over here on this end of the number line. Positive infinity is over here. So if I wanted to write this as an interval, I would go from negative infinity, we read from left to right, negative infinity, all the way to 3 parentheses. This would be in interval notation. I could also do this solution in set notation. Set notation uses squiggly brackets, right? And I would say x such that, that's what this vertical bar means, such that x is less than 3. So that's how we'd write the solution in set notation. Let's do another example. I have x is greater than or equal to negative 5. So negative 5 is part of my solution, and I need to have x values that are greater than that. So that's going to be everything over here. So we'd write this in interval notation as square bracket, right, because my endpoint is included, negative infinity, comma, positive infinity.